Hello, everyone. Thank you for coming to this talk. So the previous talk was a very good introduction or very good background information for what I'm going to present today. So today I'm going to present something called a programmable switch. Some of you might not be familiar with it, so I'll first start with introducing what programmable switch means and why we are actually doing this work. So this is a joint work with Princeton, Stanford, VMware, and Barefoot. So as you can guess, we're working with OVS very closely, and we have plans. Also, we're in progress to work with FDIO as well. So first, fast networks today, such as the ones like in data centers, are built from fixed function switch chips. What they mean are they basically support a fixed set of protocols. So when they're designed and manufactured, they have a set number of protocols that they are going to support. And since they are a set number of protocols, it's really hard to change them afterwards. However, due to that, there have been a lot of cases where you want to add custom protocols or do differently. So first of all, we want to have programmable switches because it eases adding new protocols. For example, if you think about VXLAN protocol, it took 4 years to be added to a switch. And as you can see, that's a very, very long time in the most profitable sector of the networking industry. So we want to make that much easier to do. Secondly, there's a case of removing protocols. So if you have less protocols to manage, networks are much more reliable. And as a software engineer, there's much less software to write to support each one of those protocols. And currently, data centers are already doing that. For example, Amazon is using only L3 headers to do their packet forwarding. So as you can see, these customizations are being already made, and we want to make that much more easier to do. And third, to gain greater visibility into the network. There's a great interest right now to see what the networks are doing. For example, there have been papers about packet telemetry, and also there have been products from Cisco, such as Cisco Tetration, to give you better view of the network and what is happening. So if something goes wrong in the network, you want to be able to debug it faster. Right now, we do not have a lot of capabilities to do that. So by having programmable switches, we want to make that much easier. And lastly, this is a very experimental thought, but we want to fold network functions into the switch. So if the switch could be customized to support any number of protocols, what that means is that it could basically do a lot of things such as load balancing or node discovery, and etc. And a lot of these ideas are up in the air currently, and there's a lot of research going on around it. But the idea of protocol switches is so new that there's a lot of possibilities and it's limitless. So that's one of the researches that I'm thinking into doing next. So given that, let me define what programmable switch looks like. So assume that we have a programmable switching chip. That means that a user, after the switch has been built, could customize it with set number of protocols. You could define the traditional protocols or even add one of your new protocols that you want to add. What protocol here means that just it's a packet header and packet fields that you want the switch to support. And then you could also remove the protocols, as I mentioned before. Currently, there's a lot of work in building programmable switch chips. There's ones from Intel called FlexPipe, and there are multiple startups such as Xpliant and Barefoot Networks building programmable hardware chips. However, let's look at the current modern-day virtualized data centers. In a modern-day data centers, there are VMs, and there's a hypervisor managing the VMs, and also there's a hypervisor switch. Just a brief background on what hypervisor switch is. They basically move packets between VMs and also from VM to the outside world. So as you can see, here we have 3 virtual ports and 1 physical port. these might be very simple information that you all know or may not know, so I'll just share. So as you see here, there's more virtual ports than physical ports in this design. And surprisingly, this is a data point from VMworld 2013. There's a lot more virtual ports than physical ports now. So as you can see, only having programmable hardware chip, there's a missing piece there because we have a lot more virtual ports, and how are we going to make them programmable? And a lot of people think that it should be easy to program software switches. I mean, because they're just a piece of software, you could just add new features very easily, and that's one assumption people have when I try to convey the idea of how hard to make programmable software switches. But actually, it is not that easy, and I'll tell you why it's not that easy. So a software switch sits on top of fast packet forwarding, such as the kernel modules or DPDK in this sense. And on top of that, as a developer, you have to define the packet processing logic that sits on top of it, which includes things like the parser and the match action pipeline. Match action pipeline basically means that the set of functions to match on certain headers and perform certain actions on them. And those could be very generic actions such as decrement TTL, or it could be very complex. But as a software engineer building a software switch, you have to define them yourself. And then between the packet processing logic and the drivers to do fast packet forwarding, there's specialized APIs. As you all know, there's a bunch of APIs available for DPDK to retrieve packets or even have buffers. So running the logic on top of it requires you to use those APIs. So as you can see in this design, you need domain expertise in network protocol design because you have to design how the parsers work and how the match action pipeline works. And also you need to have some expertise in kernel development or very specialized software development skills. This is not basic Java programming, as you all know. This is very hard stuff. And in order to release changes, it takes a very long time. For example, adding something to a kernel could take from 9 months to even multiple years. And we want to make that process much more easier. For example, I'll give you an example to illustrate my point. Adding a very basic TCP flag in Open vSwitch required changes in 20 files and 370 lines of code, and that's excluding all the code regarding tests. This is just to do parse and match action. And it took weeks of development and test. And if the change required, so if it wasn't a DPDK-based OVS, for example, if it was a kernel module and you needed to change the kernel module, then imagine how long that would take. So what I'm going to present today is we could do this in basically 4 lines within minutes with PISCES. Let's consider the following snippets of code. Something that looks very similar to JSON, and it just defines the header types. Here I named it TCP type version 2. And as you can see, all you need to do is add 12 bytes of TCP flag in there. And given the header, I define the parser as follows. So I extract the TCP header, and then I set the metadata for the TCP flags. And I'll tell you what those metadata means afterwards. And then and also define another header type to store the metadata of the TCP flags. So this is the actual change that we made to enable TCP flag. Okay, so the basic idea is as follows. So given a software switch and with the architecture as I described before, a very high-level architecture, what if we take the parser and match action pipeline and separate it from the software switch? And then we define the parser and match action pipeline using something called a domain-specific language, DSL. A DSL is a specialized language specific for an application domain. For us, we're going to use a DSL specific for networking. And then we build a compiler to compile the logic down to the underlying software switch. So as you can see, we could take a domain-specific language that looks like something we showed before, and then compile it down to the underlying software switch that we choose. And as you can see, this could be generalized. The idea could be generalized into different domain-specific languages, and this could be generalized to different targets. So this, the idea is not specific for PISCES. It is specific for a single language and a single target, but as you can see, the idea could be generalized to anything. Yes, so again, PISCES is an implementation with a specific domain, a specific DSL, and a specific software switch target. So for our use, we use something called a P4. I'm not sure if everybody has heard about it, but P4 is an open source language. It is currently being very active in the community, and it is a good, simple enough language to do to define the packet processing logic. You saw a snippet of P4 before, just now, which showed the parser and the match. The header fields, and the match action pipeline is defined in a similar fashion as well. So it's very easy to express different aspects of a packet processor, such as packet fields, parser action, and the match action table, as you see before. And then for our underlying software switch, we use OVS. And I'm just going to digress about the details of OVS. So given P4 to OVS, I'm going to tell you how easy it is to do our easy it is to program in P4. For example, given the entire native OVS packet processing logic, we were able to specify in just 341 lines of P4 code, as compared to 14,000 lines of C code, native C code. So you can see how easy it is for example, a network engineer to just define the packet processing logic using P4. So I'll tell you a little bit more detail about how PISCES works. So given the big picture, you basically take a P4 file as an input, and then let the compiler, our PISCES compiler, build the parse, match, and action code. Generate the code for parse, match, and action, and then we inject it in the right places that are in OVS. And given that, we run the traditional OVS compilation procedure, and it will generate the set of OVS executables, such as OFCTLs or the OVS server executables with the set of protocols that we defined in the beginning. And as you can see, the compilation procedure takes about 20 to 30 seconds, maybe, depending on the machine. So if you take a different P4 file with different set of header fields, you could just repeat the process. And since the OVS executable looks just like the ones that are running in your server currently, you could simply replace your data plane logic in a couple of minutes. So you could do that with version 2, with TCP flags, and so forth. So a question that I always get when I present this approach is, is there a performance overhead? Because P4 is a high-level language, you cannot really specify details of, let's say, compilation procedures or any optimizations that you want to make. There must be a performance overhead between a very experienced software developer who wrote all the code by hand in OVS. So what I wanted to do is show you what the performance overhead is, and if it exists, and how much that is, and that we define as cost of programmability, because we're adding some cost to gain the flexibility and ease of programming the packet processing logic. So initially, for our initial version, 0.01, on our L2, L3 echo application, which is basically a router with an access control list. For our PISCES, this is a throughput number based on, with a different set of packet sizes. Our PISCES version 0.01 versus a native OVS had a huge throughput drop, which is about 40% overhead. So people could argue that's unusual. Why would you do that, right? and you barely change the protocols once in a while. So we decided to go deeper and try to identify what the causes for the cost of performance are. So there's the CPU cycles per packet. This diagram shows how the packet travels within OVS. There's the packet parser, and there's given some checksums. You have to verify the checksum, and it goes into the match action cache. As the previous presenter talked about, there is a fast flow cache in OVS. If there's a cache miss, it goes into the match action table, and it updates the checksum. And then there's a notion of packet deparser that I will not go into detail about, but you have to deparse the packet back to the line and send it out to egress. So since this is a software switch, there's different factors in affecting the CPU cycles for each packet. And then there's also the notion of cache misses. And I won't go into details about the cache misses, but it's specified in our paper. So there are multiple factors affecting CPU cycles per packet, and I'll discuss a couple of them. First is the fully specified checksum, and second is parsing unused header fields. So when a packet comes in, the P4 specification doesn't really tell you what to do with the checksum. So it will run checksum verify on all of the 12 fields of an IP. And then similarly, it will update the checksum using all of the fields on the IP header. However, assume that the user is doing very simple operations such as decrement TTL on your switch. Then just updating the checksum on every 12 field just doesn't make sense. And in OVS, there's already a notion of incremental checksum implemented. So we identified that, and basically what we did is did an incremental checksum on the TTL value. Second is selective parsing. So assume that your header contains L2, L3, and L4 headers. However, your match action pipeline only uses L2 headers. So it doesn't really make sense to parse all of the 3 headers that are not going to be used. So our compiler identifies the set of headers that are not used, and then it will selectively not parse them. And as you can see how this could be an optimization that improves performance. So for our throughput on the L2, L3 benchmark application, after the optimization, this is, in order to shorten the graph, I'm just going to show you the results for the 64 packet sizes for 64 bytes, but on our paper, there's more details. So aside from incremental checksums and selective parsing, we've done multiple other optimizations, and the details are also in the paper. We started off with about 8 gigabits per second. And after incremental checksum, which gave a huge boost, it went a little bit above 12 gigabits per second. And then after that, it was a very small incremental addition. However, one thing to notice here is that the header memory locality, which I haven't discussed, is an optimization that humans cannot do very easily. So in the end, we had a performance overhead of only 2%. But since some optimizations are made such that it is not currently in OVS, we are hoping to bridge the gap closer and even exceed it at some point. So what I wanted to share is that adding programmability to your software switch doesn't really have a huge performance impact like many others might assume. So in summary, so we have a PISCES OVS, and it is a tool to quickly develop and deploy new packet header formats. So as you can see, and you could imagine multiple applications for this for different data centers, and mostly this is for data centers using custom protocols and custom headers. And with hardly any performance cost. So you're gaining a lot of flexibility with any performance cost. So you could learn more and try PISCES here. PISCES is basically customized version of OVS, as I mentioned before. So you could deploy them in your custom setup, or even for Mininet setup, and try different setup protocols and try different applications to run on top of it. This version currently is a research version. However, we are currently working to add PISCES into the mainline OVS repository incrementally. First, by defining the configurations of OVS using P4 and adding match action pipelines and so forth. So you could expect this to be an OVS pipeline by the end of the year. And also, this entire presentation, as well as the paper regarding this, is on this year's SIGCOMM as well. So if interested, you could shoot me an email, or meet me afterwards, and I could send you the links for where to find the paper and other information. And also for future works, I'm currently working on similar approach to do in FDIO as well. If you remember, we're adding a new plugin that does the parser match action pipeline and trying to find ways to optimize it in VPP as well. So if your data center only uses VPP, then in a couple months, it'll be out, and I'll be releasing it soon too. Okay, so if there's any question, that concludes my talk. Yes?
Justin, sir. So having consumable APIs to program for gameplay, great thing. Mm-hmm. So having this flexibility and controlling the hardware, which is the end product of Barefoot Network, for example, gives you ability to know exactly what you're programming. Because people who've been building this stuff for a long time, we know there's no free lunch in FastPass.
Right.
You run out of resources, you either recirculate or you go into slow pass.
Yeah.
So again, if you have flexible NPU such as Barefoot or something Cisco is doing, you could do a lot of stuff. If you go on Intel, you don't really know. So how do you know that the result of compilation of your P4 high-level API will not push your traffic into slow pass? Is there any correlation between intended state and what your hardware is capable of?
Right. The question about slow path in OVS is really hard for us. So given OVS fast path, so you know what's coming into the line. So the fast path in OVS is very specialized for like exact matching of the headers, for example, like certain values for your header. But for P4, you could basically program it any way you want. So you can't really pinpoint on what's going to happen on the fast path. So we are looking into adding new changes for that, but for now, all of the work here is done on the slow path.
So you compile and pray.
Yeah.
You're not going to hit slow.
Yeah. Yeah. Any other questions? Oh, yes.
I've been away from, haven't paid much attention to PISCES and P4 much in the last few months, so forgive my lack of full understanding. But you talked about the P4 compiler.
Yes.
Did you guys write, did P4 people or Barefoot wrote that compiler?
Right, so there's a bunch of compilers out there. What we use is the one that is provided by Barefoot. It's called a P4 behavioral model, which is a compiler for the older version of P4, P4 version 1.0. Now, there's multiple compilers out. I know that Barefoot has at least 2 or more, and there's a bunch of them from Cisco and other users as well. But ours is like somewhat of a so we wrote our somewhat of a compiler because what the Barefoot compiler generates is a set of JSON objects. So we use the JSON objects to generate C code, and we use C templates to do that. So I guess in some way that's a compiler from JSON to C. Yeah.
Okay. Thank you.
Any other questions? Okay. Thank you very much.